Okay, so now we're going to consider an example which involves all of the different forms of energy storage that we've talked about: kinetic energy, gravitational field energy, spring energy, and thermal energy. And we're going to solve this problem. It's kind of a rich problem. We're going to solve this problem using both the idea of energy storage. In other words, the change in the total energy of an isolated system is zero. When one goes down, something else goes up, without any regard to transfer of energy. And then we're going to solve it again using the idea of transfer of energy. So we're going to have blocks in motion. They can store kinetic energy. Forces acting will do work. We'll transfer energy to those blocks, and we'll use the we'll use the work kinetic energy theorem to solve it. And I want to really sort of emphasize in this particular problem here that those two methods of solving these energy related problems are identical. Okay? They say exactly the same thing. Right. And so now this example is a little bit artificial, but it's nice because it involves all these forms of energy. So it involves an inclined plane. So there's an inclined plane like this. And the plane is inclined at an angle theta above the horizontal. And there's some blocks involved. So there's a block of mass little m on the incline, and there's a coefficient of kinetic friction between the block and the incline. This block is going to be sliding up like this, so the incline will exert a force of kinetic friction down the incline on block little m. Okay, and then that block little m is attached with a rope over a pulley, a massless, frictionless ideal pulley, to a larger mass, big M. Okay, and so the idea is that big M is sufficiently large so that when you release these masses from rest, then big M is going to move down and little m will move up the incline. Okay, now we're going to add one more element to this, and that's going to be a spring. Okay, so this is the ground. We're going to add a spring, and the spring will be of exactly the right length so that in its uncompressed state and unstretched state, in its equilibrium state, it reaches from the ground up to the bottom of mass m. So right now, initially, the spring is neither compressed nor stretched. Okay, so that's our situation. And the spring has a spring constant k. Okay. Now the question, we're going to start this system from rest. So start at rest. Okay. And we're going to release these masses. And what's going to happen is mass m will fall down, mass little m will go up. But as mass big M falls down, the spring will get compressed, and so it will exert an ever stronger force on big M until eventually big M comes momentarily to rest, and little m at the same time comes momentarily to rest. Now, if we left it after that point, then big M would bounce back up and there'd be some oscillation. We don't care about that part of it. So what we're interested in is what distance d does big M need to fall down through, and at the same time little m move up the incline. What distance d such that big M and little m momentarily come to rest for the first time after being initially at rest. Okay, so we're interested in what is d to come to rest again the first time. Okay, and now oftentimes we have masses in our problems, and we take as one system the mass, and everything out, and the rest is everything else. Okay, and this system, or in this problem, we're going to take both masses together that are connected with that rope. We're going to take those two masses together as the things which can absorb or store kinetic energy. So we're really talking about this little m, big M system, which I just sort of unwound like this, straightened out the string here, a little m, big M system as one sort of subsystem, and then everything else is what these masses interact with. So these masses will have forces acting on them, and those forces acting through displacements will transfer kinetic energy to that little m, big M system. Okay? Now, because we're going to for sure need the force of kinetic friction, and later on we're going to be solving the problem using the work kinetic energy theorem, which means you have to figure out the work done by all the various forces, we need to identify all the forces. So we should draw a free body diagram, so let's do that right away. So we'll draw a free body diagram for little m. That'll be the more, well, they're both equally important, but the little m is a little bit more complicated. Okay, so on little m, there's a field force, which is gravity pulling. So let's label this as little m. And so there's gravity pulling down, which is little mg. Okay, and then there are contact forces. Okay, and so the contact forces are certainly the string, the rope is touching little m, and let's suppose that this string, this length of string is under tension T, then automatically, because this is a massless ideal, frictionless ideal pulley, the tension in this section of rope is also T. Okay, and so the rope is going to exert a contact force on little m, which is in a direction up the incline. So like this, so we have a tension T, and the angle here is theta. And also, the incline, the mass touching incline, the incline will exert a force on m, and so there will be a normal force, which is in this direction. It's a normal force, and this block, little m, is going to be sliding up the incline, and so there will be a force of friction, in this case kinetic friction, opposing that motion up, so it'll be down the incline, and so that's in a direction opposite to the tension. Okay, so there's a force of kinetic friction on block little m. Okay, so we're going to use that diagram. And then also there's a free body diagram for the mass big M. And for the mass big M, what we have is there is a field force, gravity pulling down, which is bigger than this guy, because big M is going to be probably bigger. So it's going to be big mg pulling down. That's the field force acting on big M. And then what are the contact forces? Well, there's a rope touching it at the top, and that rope is under tension, so it will exert an upward force on big M of magnitude T. But there's also another upward force, which is the spring. The spring is also pushing up. So there's a second upward force, which is the force that the spring exerts on big M. Okay, so we have these two free body diagrams, and just to double check, remember that whenever you have systems interacting with each other, here's an object in motion, here's an object in motion, but they are exerting forces on each other. They are connected. They're connected by this string. Okay, and so there's an action-reaction pair of forces here. Okay, from this diagram and that diagram. Okay, so yeah, I think that's basically it. What else? Oh, we should also figure out, just while we're at it here, let's figure out what the force of kinetic friction is. Okay, so for the force of kinetic friction, that's easy. So the force of kinetic friction, that's acting on little m as it's sliding up like that, well, that force of kinetic friction is going to equal the coefficient of kinetic friction, mu k, times the normal force, how tightly those masses are pressed together. So we need this normal force here. And so if we look at this, we recognize that there is no acceleration in the direction perpendicular to the incline, so the net force perpendicular to the incline better be equal to 0. And so the only forces that are perpendicular to the incline are the normal force that way, and this component of the weight. And so that component of the weight has to equal the normal force. So the normal force is that component of the weight, and when theta goes to 0, that becomes the full mg. So it must be a cosine of mg. So it's equal to mu k times the weight mg times cosine of theta. Okay, so that little bit will come in handy. And it's also important to note that that force of kinetic friction is constant. None of these things are changing with time. So this is constant. And that's going to be nice, because remember, when the magnitude of the force of friction is constant, we have a very simple expression for figuring out what the change in thermal energy is, how much thermal energy is generated by that friction force acting through a displacement. Okay, very good. Okay, so now we're going to solve this problem in our two usual ways. So the first way is we're going to think about energy storage mechanisms. Okay, different ways in which energy can be stored in this system. And so what we know is that the total energy, whatever it is, it's stored in various forms. That can't change. Total energy of an isolated system never changes. And so let's identify what are the various forms or ways in which energy is stored in the entire system. So one way for sure is these masses are in motion. Those masses can store kinetic energy. So there might be a change in the kinetic energy. Kinetic energy might go down and others go up and so on. Okay? And then, so another form of energy, what order do I read this in? Also, we have a mass, big M, going down. That means the gravitational field energy will be going down. We have little m riding up the incline, so its height is changing, so that will increase the gravitational field energy. So there could definitely be a change in the amount of energy stored in the gravitational field. Okay, and then another form of energy here is we've got a spring. That spring is initially relaxed, and so it just has its sort of constant value, its minimum value. But then as that spring is compressed through a distance d, there will be energy stored in it. How much? 1/2 kd squared, the amount that's compressed, by which it is compressed, squared. Okay, and so there is definitely going to be a change in the spring energy. And finally, we've got some friction involved here. So as that block little m slides along the incline, there's friction. Rub your hands together. Things heat up. You're going to generate thermal energy. Okay? So remember that energy is always conserved. Whether you have friction or not, it's always conserved. And you account for it by thinking about thermal energy. Okay? That's one of the ways in which nature can store energy. Okay, so very good. And then we can think about this. For example, change in the kinetic energy. Well, let me see. You started at rest, you let the system go, and big M fell down until it became momentarily at rest again, and little m momentarily at rest again. So you start at rest, you end rest. So the initial kinetic is 0, the final kinetic is 0, 0 minus 0, the change is 0. Okay, so this one is 0. The change in the spring energy, so that's obviously going to be positive. It started out in the relaxed position, minimum energy is 0. If we take that minimum to be 0, it's just going to increase when it's compressed. So that's going to be positive. Thermal energy that's generated by friction is always positive. Okay, change that thermal energy is going to be positive. And so it must be, that's 0. So here, two positive numbers plus that thing has to equal 0. So this must be negative. So the change in the energy stored in the gravitational field must be negative. The gravitational field energy must go down. And where does it go? Well, it goes into increasing the energy in the spring and in generating thermal energy. So that goes into that and that. Now, when we're talking just about storage mechanisms, we don't care about how that energy is transferred. We just care that the total, there's no change in the total. Okay, very good. Okay, so now let's work out the first term here, the change in the energy stored in the gravitational field. Now, in general, change in the energy stored in the gravitational field is positive mg times the change in height, height final minus height initial. So when height increases, when the height of a mass increases, the change is positive. So in this case, we have m moving up. So there's definitely some upwards motion. So it's going to be positive mg times the change in the height. Remember, as far as gravitational field energy is concerned, it doesn't matter how much horizontal motion there is. So this motion up the incline has some horizontal component. What we're really interested in is just the vertical component. So we're interested in the vertical component of that hypotenuse d. And so this angle here is theta, and so d cos theta is the horizontal, d sine theta is the vertical. So the vertical displacement up is d times sine theta. Okay. Now we have another mass, which is moving up and down. In this case, it's moving down. Okay, and so it'll be positive mg positive big M G times the change in height. Well, height final minus height initial is negative D. Okay, this is negative. Okay, so we have that. And just to sort of just point out that this change in the gravitational field energy must be negative, so this term must be bigger in magnitude than this term. And in fact, what we're going to find is that it must be, this is not just, a tiny bit bigger. It must be significantly bigger, somewhat bigger, because there's also a force of kinetic friction pulling back there. And so we'll discover that at the end. But basically, this guy over here has to be negative, for sure, and somewhat negative. Okay, and then the next is the spring. We have a spring which is being compressed, and so there's a change in the energy stored in that spring, in the electrostatic field amongst all the particles in that spring. So the change in the spring energy, so spring energy is 1/2 kx squared. It's positive, plus this arbitrary constant, or this zero constant. So the change is going to be positive 1/2 k x final squared, how much it's been compressed, squared, so that's d squared, minus sort of the x initial squared, and x initial is 0. It originally starts in the equilibrium position. And so the energy, the change in energy stored in the spring is positive 1/2 kd squared. So if d is 1 meter, there's some change. If it's 2 meters, it's 4 times as much energy stored in that spring. So the energy stored in the spring increases quadratically with the amount of compression or stretching. Okay, so we have that. And then we also have delta E thermal. So there's a change in the thermal energy. So there's been some thermal energy, this is positive, and there's some change in the thermal energy, which also has to be positive. And remember that the change in the thermal energy due to friction is just, if that friction is constant, then the change is the negative of the work done by friction, and if the friction force is constant, then the work done by friction is just the magnitude of the friction force, which in this case is Fk, times the distance that it travels through. That's negative. And so the change in the thermal energy is the negative of that, so that's positive. So the change in the thermal energy generated by friction, the increase in thermal energy is always positive, and it's the magnitude of the constant friction force, Fk, times the distance that the mass moves through, its actual path length. In this case, the path length is the same as the displacement, it's just d. So it's just positive Fk times d, and we've worked out conveniently what Fk is. It's just this. So it's mu k times this, Fk is mu k times little m g times cosine of theta times little d. So we'll stick the little d in there. Okay, so looks like that. And then finally what we do is we just add all of these up. That's 0. We add all of these up, and they should all add up to 0. This positive thing, that positive thing, plus that negative thing. Okay, and so when we do that, I'm just going to write it over here. We're always sort of short of room. So 0 equals 0 plus the change in the gravitational field energy, which is mg. I wonder if I should simplify this a little bit. In fact, okay, maybe I'll just do it this way. Okay, so I'm going to do it in a little bit different order. So I'm going to write down first the change in the energy stored in the spring. So that's positive 1/2 kd squared. Okay, and then we need to add this guy and this guy. And I'm just going to sort of simplify things as I did here in my notes. So you can see that there is a factor that's common when I add this to this. One thing that's common is little g times d, little g times d, little g times d. So I'm going to factor that out immediately. And there's a negative little g times d times a bunch of junk. So little g times d, negative little g times d, there's a positive capital M. And then g times d, negative little g times d, there's a negative little m sine theta. And then in the last one here, this is a negative little g times d times negative mu k m cos. So negative mu k m cos theta. Okay? Yes, that's right. Okay, so very good. So 0 is equal to the sum of these two things. Now, you can see there's a d squared there, and we're trying to solve for d, trying to figure out how far big M falls down before it momentarily comes to rest. We're solving for little d. This looks like it could be a quadratic equation in d, but fortunately both terms, this is a d squared and that has a d, so, and there's a 0 on the other side, and so you can cancel off one of these d's. This d squared becomes d, and this d disappears, and now it's an equation that's linear in d. So then you can just solve for d. D is basically this junk divided by 1/2 k. Okay, so when you solve for that, what you end up with is that the distance that the whole system moves through before momentarily coming to rest again turns out to be 2 times g divided by spring constant k times big M minus, and you can factor out the little m here, minus little m times sine theta plus mu k times cos theta. Okay, and so that's our answer. And then, of course, as soon as you get an answer, what you do is you stare at it and you see whether that thing makes sense. So, for instance, if you just look at the outside here, if you're in, say, on a planet with a stronger gravitational field, then there's a greater force, gravitational force on big M, and so the spring is going to compress more. So if you make G bigger, then D gets bigger. If you make the spring stiffer, then the distance these masses will move through will be less. Okay, so making K bigger makes D less. K is in the denominator, so that makes sense. Then you look at this thing and you say, well, basically we need D to be positive. Uh-oh, there's a minus sign there. So what that basically requires is that big M needs to be bigger than this stuff. So roughly, big M needs to be bigger than little m sine theta, even if it's frictionless, mu k equals 0. Big M needs to be larger than little m sine theta, because basically there's a gravitational force here, and there's the component of the gravitational force here, which is a weight times sine theta. Goes to 0 when theta goes to 0. And so there's a tug of war here. So even if this is frictionless, you require, in order for this to move this way, you require big M to be bigger than little m sine theta. And then there's an additional factor here that says if you've got friction involved, as this thing slides, friction is a force that way, and so you're going to need big M to be even bigger. Okay, so there's a minus something even more. So big M needs to be bigger than we talked about before by this additional little m times mu k cos theta. Okay, that's basically related to this idea that delta mu gravity has to be negative. Okay, so at least this has to be negative, but it has to be not just slightly below 0. It means it needs to be a little bit, a little bit negative. Okay, to account for this mu k term. Okay, so great. So so we have solved the problem using conservation of energy, thinking in terms of storage mechanisms, without any regard to how energy is transferred between those various ways of storing energy. So now the next way we're going to solve it, as usual, is by thinking about how energy is transferred. Okay? And so now what we're talking about here is a system of masses. It's not just one mass now, it's two masses, little m and big M. They're in motion. Okay, and so in principle, there are forces acting on little m and big M, and so those forces, as they move, they are going to, there are forces acting through displacements, and they are going to transfer energy, kinetic energy to little m and kinetic energy to big M, and so on and so forth. Okay, so yeah. So our system is actually two masses. We always have to be thinking about two masses. And so when we think about energy storage, energy transfer mechanisms, then we're talking about the work kinetic energy theorem. So all of the total work done by all of the forces on little m plus all of the forces on big M as they move through their displacements, that total work done that net work done by all those forces has to equal the change in the kinetic energy now of both masses together. Okay, but in this particular problem, we know that the change in the kinetic energy is 0. They started at rest, they ended at rest. So 0 minus 0 is 0. So all we really need to do is work out the total work. Okay, and that total work is forces on little m and big M through various displacements. Okay, so there's a whole bunch of forces here. Okay, so the total work is going to be, let's write it out in, say, this order. It's the work done by the gravitational forces, little mg and big mg on these masses when they do that. Okay, plus the work done by the spring force. So on big M, there's a spring force acting. It's pushing that way as the displacement is that way. So that's going to do work on part of that system, big M. And then work done by the force of kinetic friction. There's a force of friction acting on little m. That's that guy. That's going to be doing, that guy. That's going to be doing some work. And what else? Oh, you know what? We should also include, as little m moves up, there's a tension force acting. And as big M moves down, there's a tension force acting. Okay, and so those tension forces are also going to do work. And that's actually a somewhat interesting point here. So it's plus the work of the tension force T on little m plus the work of the tension force T on big M. As m goes down, tension is up. So this is tension on big M. Okay, so now let's think about this for a second here. So the work done by the tension force T on little m, well, what's that? Whatever that tension is, it's some value, the work that it's going to do is, now the tension might not be constant, but let's just assume for the moment that it's constant. Okay, so the work done is just going to be, it's force dot displacement. So the force that the tension exerts is that way, the displacement of little m is that way, and so force dot displacement is positive. It's just positive the tension times the displacement. So this guy here is positive the tension times the distance d that it slides through. Okay, if t were constant. It's not really constant, but the point is it's positive something. Okay, and then similarly, if we look at the work that big T, the force big T pulling up, does on big M as it falls down, well, now we have the forces in that direction, vector dot product the displacement in that direction, so it's going to be negative. Okay, the angle between the force and the displacement are 180 degrees, and so it's the magnitude of the force, tension, times the displacement. Okay, so what's interesting about this is these work terms automatically cancel each other out. Okay, and that's because if we look at our system over here, this is our system, and yeah, big M exerts a force on little m through a tension T, while little m exerts a force on big M through T in the opposite direction. So as this thing slides this way and that way, the energy transferred between is 0. Okay? So the string actually plays no role in this. It just holds those two masses together as one whole system. It's as if they were just sort of like glued together. Okay? So it plays no role. That's kind of interesting. Okay, so now what? So now we need to work out these work terms. Okay, so there's the work done by the gravitational force on both of these masses, and because I'm going to do this sort of pictorially. So the work done by a force, usually that is an integral, but when the force is constant, then it's just simply the constant force vector dot product with the displacement, the finite displacement. So the work done by gravity on little m, what's that going to be? How did I want to write this? It's going to be the constant force, the constant gravitational force acting on little m, vector dot product with its displacement. So the constant gravitational force acting on little m is a force of magnitude mg pointing straight down. And we want to vector dot product that with the finite displacement of little m. And the finite displacement is of length little d, in a direction up the incline. So it's a vector of length little d, and it's pointed up the incline at this angle theta. So it's the vector dot product between those two vectors, okay? Excuse me. Plus, talking too much today, plus the constant gravitational force acting on big M, okay, that's a force of magnitude big mg pointing straight down, vector dot product with the displacement. The displacement of big M is a vector of magnitude little d pointing straight down. Okay? And so if we work this out, yeah, I guess I'll have enough room if I do it down here. Excuse me. Okay, so this is going to be, because they are the angle between this vector and this vector is greater than 90 degrees, this one is going to be negative, and it's going to be an mgd, and then there's going to be a sine of the angle theta when you take the vector dot product between that guy and that guy. It's really cosine of this full angle, which is the same as sine of this angle theta here. Okay? So I think I have that right. Sine theta, that's right. And then this one is going to be positive. They're both in the same direction. It'll be positive big M G D, and that's it. Right? And so I want you to notice something very important here. I think we've seen this before. And where did we see it before? We saw it right over there. Here is a positive little mgd sine. Here's a negative little mgd sine. Here's a negative big mgd. Here's a positive big mgd. That's the same as that, except for a minus sign. So the work done by gravity is, of course, negative the change in the energy stored in the gravitational field. So if you drop something, gravity is pushing in the same direction as the displacement, and the work done by gravity is positive. But that means that energy is leaving the gravitational field, and so the change in energy of the gravitational field is negative. So work done by gravity is the negative of the change in energy stored in the gravitational field. Okay, let's work out the next one, the work done by the spring. Okay, so the work done by the spring, so in that case, because the spring force is not constant, we really have to do that integral. And we did that integral already, so let's not mess this up by doing a whole integral. But remember that at the end of the day, the work done by the spring is, just like the work done by gravity, is the negative of the change in the energy stored in the gravitational field. The work done by the spring will be the negative of the change in energy of the spring. And change in energy of the spring, because energy of the spring is a positive 1/2 kx squared plus a constant. The change in the energy is positive 1/2 k. Change in the energy is positive 1/2 k times the change in x squared. And so the work done by the spring will be the negative of that. So the work done by the spring is negative 1/2 k times the change in x squared. So that's negative 1/2 k. And so this means x squared final minus x squared initial. So in the final position, the x position, how much it's been compressed from equilibrium, is d. So that's d squared minus the initial x squared. Well, the initial x is 0 because the spring is initially in its equilibrium position. Okay, so we have that. And then again, we look and we see, where have I seen that before? Well, I've seen it over here. The change in the energy stored in the spring is positive 1/2 kd squared. Here's a negative 1/2 kd squared. So this is negative the change in energy stored in the spring, which is what I just said a minute ago. Okay, so we have that. And then the last one is the work done by friction. The work done by the kinetic friction force. Okay, and that's that kinetic friction force that's acting on little m. So the displacement of little m is that way, the friction force is that way. The work done by friction, that is going to be negative. So the work done by friction is, well, because the friction force is constant, the work done by the friction force is just that constant friction force, vector dot product with the displacement. So let's use this similar sort of notation here. So it's the it's the constant force of kinetic friction. So that is a force of magnitude Fk, which we worked out before. Fk is this thing. And it's pointing down the incline like that. And we vector dot product that with the displacement. And the displacement is up the incline of magnitude d. So it's a vector of length d up the incline. And these two vectors are in exactly opposite the directions, and so their dot products are going to result in a minus sign. So this is a minus Fk times d. Okay. So again, where did we see that before? Oh, the change in the thermal energy is positive Fkd. It increases, and so that's negative the work done by kinetic friction. So this is the work done by kinetic friction is negative the change in the thermal energy. Okay, very good. And so now we're trying to solve this problem using transfer of energy, and we're saying that, yeah, all of these forces acting on these masses, as that guy moves up and that guy moves down, they all do work. They all transfer kinetic energy to this system. Now, of course, at the end of the day, the total transfer is zero because they start at rest and end at rest, okay? But what we want to do here, let's just keep the change in kinetic energy not zero yet. So we're saying that the change in the kinetic energy is equal to the total work done. So the total work done is work done by gravity plus work done by spring plus work done by force of kinetic friction. Okay, but that work done by gravity is negative the change in the gravitational field energy. Work done by spring is negative the change in the energy stored in the spring. Got a minus sign out there. The work done by the force of kinetic friction is negative the change in E thermal. Okay? So what I can do is I can, plug all these things in here and find and solve for D, but you can see immediately that this equation, work total is equal to change in kinetic, is exactly the same as conservation of total energy, thought about as change in the total energy being zero. Because if I take all three of these negative terms to the other side of the equation, what I have is delta K, okay, plus delta U gravity, plus delta US, plus delta E thermal equals 0. And so this statement of transfer of energy is identical to the statement of storage of energy. Energy conservation can be thought about equivalently both ways. All that we're really doing is we're saying, look, we've got some system like this, okay? If, which is often the case, we have masses in motion, they can only store energy in the form of kinetic energy. And so we have, blocks and such, okay? And they store energy in the form of kinetic energy. But then in the system, there's all other kinds of forms of energy. So there's, gravitational energy, spring energy, etc. And so all that's happening here, we can think about it as, yes, the changes in these guys plus the changes in this guy all add up to 0 within that isolated system, or the work done by all of these changes. So there's changes in energy here that corresponds to energy flows, energy transfers. All of those work energy transfers change the kinetic energy. You're saying exactly the same thing. There's no difference. In some problems, it's easier to solve using this. In fact, most of them it's easier to solve using this. But in other problems, it's easier to solve using this method. But this method has the advantage that it often shows up interesting things about how energy is transferred, energy transfer mechanisms. Okay, so very good. So I hope that this example, it's meant to sort of involve all the forms of energy that we've talked about, and especially show in detail how you use this, and how you use this, and how that they are actually equivalent. Okay, very good.